Hello, I am going to make a short video of exercise 2. Well, first of all, I have to open Stata. And well, I have my do file already done and finished, so I will open it. Okay, perfect, exercise 2. I have here, we have to open import the data using the same instruction as in exercise 1. Okay, here we have it. Perfect. I will compress to increase the performance of my PC, and well, then I will start. Exercise 2.1. Research claimed that firm size possibly moderates CEO pay, and as a result, CEOs might engage in acquisitions to increase the size of their firms. One way to test this claim is to run a regression of logarithm of total compensation on age, sales, CEO dummy, and the interaction between CEO dummy and sales. What does a coefficient on the interaction term measures? Well, first of all, we have to generate the variable logarithm of total compensation and the interaction term. We can do this by using this command again, or we can just do it with a menu bar over here. I will run my do file, it's easier. Okay. Generate, and then I will generate the interaction term. Perfect. I'm just going to make a quick check. Here we have the interaction. Here we have the CEOs, and here we have the logarithm of total compensation. Perfect. Okay. Well, now we can proceed with our regression. Here we have the regression. Here we have our interaction term. Okay, perfect. And what interaction terms captures is the effect on total compensation of sales when the worker is a CEO. The coefficient will indicate if this relation has a significant or not positive or negative effect on compensation. In this case, the corresponding coefficient is significant using a significance level of 0.05. We can see here. However, the corresponding coefficient is almost 0, even though it is positive, indicating very little effect on total compensation for a CEO when his sales are increased. No? Here we see that it is positive, but it's a really small number. Okay, so there's a positive effect that shows the interaction term of being a CEO with sales. Okay. Exercise 2.2. Jan is a 50-year-old CEO working at a firm with sales equal to $1 million US. What does the regression predict for his compensation? Bert is a 50-year-old non-CEO also working at a firm with sales equal to $1 million US. What does the regression predict for his compensation? What is the predicted difference between Jan and Bert's compensation? Use the model from equation 2, part 1. Okay, perfect. So we have to use these coefficients and substitute the information of Jan and Bert, and then get the difference. So, well, this is just choosing our calculators and making these operations. Jan, well, the dummy variables over here. Okay, I will just follow here. The logarithm of total compensation is equal to the constant plus the effect of sales multiplied by 50, the age of Jan, plus the coefficient of sales multiplied by 1, plus this number, the coefficient of the CEO dummy, because he's a CEO, multiplied by 1, plus add the interaction term multiplied by 1 because he is the CEO. This one is because he increased in $1 million his sales. Okay, so we get this number, logarithm of total compensation. It's equal to this number. We have to make this operation to get rid of the logarithm, use the exponential of the number, and we finally have this number, 1920.561 units. Well, the units are thousands of US dollars. Sorry, I will show it quickly. Okay. Yeah, we have seen this also in the previous exercise. In thousands of US dollars. Sorry, thousands. Okay, perfect. We can continue. Cool. Bert, we have to do the same, 1 million, but he's not a CEO, so these dummies are 0. So we get this number at the end of the operation, and to get the difference, we have just to do the difference, rest 1920.561 minus 793.287. It's equal to this. So this is the predicted difference, 1,127.274 units in thousands of US dollars. Okay, perfect. We can continue with exercise 2.3. Make a plot to illustrate the interaction effect on question 2, part 1. Well, I chose to make this one. Well, here we have the graph, the interaction term, and the logarithm of total compensation. I'm going to close it. Okay, we can continue with exercise 2.4. Research claimed that characteristics specific to the individual, as opposed to firm or industry-related characteristics, are not important in determining compensation. One way to test this is to use the regression model with a logarithm of total compensation as dependent variable and appropriate right-hand side variables. Estimate a model to test this claim and explain. Okay, perfect. Well, the variables related to specificity of the individual in the dataset are gender, age, tenure, and CO dummy. These are characteristics of the individuals, not of the industry or the firm. Okay, so we can make a regression including these variables and find out if something is significant. If you want to include the variable corresponding to gender, we have to build the following variable. Yes, this is because on our dataset at the beginning, we had gender as a string variable, and well, we need a numerical variable to see if to use it in Stata, no? To use the dummy variable. Okay, perfect. Continue. So we have to use these comments over here. Generate. Okay, something is wrong. Sorry, my computer is working. Perfect. We have to run these two commands. Generate. Okay, first I will show the effect quickly. Now we have here gender, but we have here nothing because, well, for females we haven't done the second command. Okay, then we run our second do file, our second command, replace. Now we get it correctly. So males get a 1 and females get a 0. That's our dummy variable. Okay, with this procedure we had transformed a string variable into a numerical variable, and now we can do a regression with our dummy variable included. So I will regress this one over here. Perfect. Our regression is over here, and as we can see, gender 2 is significant. at the 0.50 level of significance. Therefore, variables related to a specific characteristic of an individual are important. Well, that's my conclusion. And I have proved it with statistics. Okay, so let's continue. Exercise 5.5. Let me see if I cannot say anything else from here. Okay, CO-dummy is also significant. So, well, that's also a characteristic specific from an individual. But well, I continue with 5.5. What other variables besides those used in the models above do you think would be needed to explain variations in executive compensation? Discuss at least 3 additional variables that might explain variations in executive compensation. Well, I put these 3. There might be much more, but I chose these ones. In many companies, the CEOs are the owners of the company. I think CEOs that are owners of the companies should compensate themselves more than normal CEOs. We could model this with a dummy variable or the percentage of the shares owned by the CEO. Well, at least here in Mexico, there are a lot of family businesses, and of course the owners are the CEOs, and they compensate. I think they should compensate themselves a lot more than CEOs that are not the owners of the company. So that's why I included this variable. And second, we could also include profits. The data set does not include profits, which are very important to measure the compensation of CEOs. We just used sales, and this was just to try to see the size of the company to capture that, but it's more important than sales, the profits. If the CEOs make a lot of profits, they should be compensated more. So, well, this is very logic and obvious. So profit is a good variable to include. And finally, we could also use number of employees to represent firm size. It is somehow equivalent to sales because it tries to capture the effect of firm size, but it is still different and very representative. Some companies might have a lot of sales, but they might not be, well, I think employees is another variable that can represent the size of a company, and it is very important. Okay, so thank you. This is exercise 2 on a video, and well, see you probably next time. Bye bye.